Hey everyone, today's lesson is sections 4.5 and then a little bit from 4.6. Both sections cover inverse functions, and I'm guessing this will be somewhat of a new idea for you. Before we start in with inverses, however, I want to just make sure you're good with the last couple days. You will have a Schoology quiz at this point, and it's labeled 4.1 through 4.4, and you just take the quiz right on Schoology. You get one attempt. It does go in the assessment category, so that's why we're just giving you one attempt, right or wrong. You can take as much time as you need. So if you don't do it today or you start it today and finish it tomorrow, that is fine. So off to the side, I have solve the seventh root of x raised to the fifth equals negative 4.8. So if you recall from the last couple days, to undo a radical, you can raise it to the seventh power, and to undo a power, you can root a fifth root. Or all in one step, and probably a little more efficient, is to write the problem from radical form to rational exponent form. So you know your power is your numerator, radical is your denominator. And then if you're going to solve for a power, if it was x squared, we would just square root. And now, rather than, again, doing it in two steps, you can just raise the 5/7 to the reciprocal power of 7/5. And of course, if we do that on the left-hand side, we want to do that on the right-hand side to balance. And now you would pick up your calculator and you would type in negative 4.8 to the 7/5 power, and I got negative 8.9895 if you want to round at that point. You could go back and check your answer. I put parentheses around my negative 4.8. It's not necessary in this case since both my power and my root are odd, but it would absolutely be necessary if my power was even. And if my root was even, I wouldn't be able to do this because you can't even root negative numbers. So just to be safe, I would, anytime you're raising a number from here, this step to the final step to a power, just encompass that in parentheses to be safe. All right, on to inverses. Here is your formal definition of an inverse. So if you have a relation, or a function for that matter, if you're asked to find the inverse of a function, you switch the coordinates of the ordered pair. So we'll start out real basic. If this is my relation, you can see the set of points. If I'm going to inverse those, that relation, I literally flip x and y. So now my x coordinates become what my y coordinates were, and my y coordinates become what my x coordinates were. Okay, so just a really basic example of what an inverse is. Okay, so you flip x and y. Now, if it's in an equation and not a set of points, these are the steps in finding the inverse. So first step would be you exchange x and y. So you literally switch them. In fact, I will go down looking at this example here of y equals 2x plus 1. I'm going to switch x and y. Remind yourself f of x is really just y. So your y is now here and your x is now here. Okay, that's step one. Step two is solve for y. Okay, so step two is where the work is, clearly. So if you're going to solve this equation for y, you're going to subtract 1 over first. Okay, so subtract 1. And then you're going to divide both sides by 2. So it's very easy math, nothing you can't handle at this point, right? Divide both sides by 2, and you end up here. My recommendation to you is to break this fraction into two parts. So it would look like this, obviously 1/2 x minus 1/2 down here. Also note the notation. When you find the inverse notation is f to the negative 1 of x. Okay, and I can scroll back up here. Step number 3, don't forget the function notation. And function notation, this looks like a negative exponent, but it's simply just notation. So you aren't simplifying anything any further. Like this function is the inverse of the original. Okay, so this linear function and this linear function are inverses of one another. All right, let's look at another one. So find the inverse, and then we're going to kind of dive more deeply into it and take a look at how it graphically looks as well. So actually, why don't you pause this one and see if you can find the inverse first. All right, so step one, switch x and y. That's the easy step. Then you solve for y. So I subtracted 6 first. And then you're going to divide everything by -3. And I would simplify that a step further. So when you divide everything by -3, you get -1/3, and then -6 divided by -3 would be +2. So just be careful in your simplifying, of course. Okay, now I do want to take a look at this graphically because I know you will be asked to graph these. The red is the original, the blue is the original, the red is the inverse. Again, note the inverse notation, right? F to the negative first. When you take a look at these on your graph, you can feel free to grab your graphing calculator. These would be pretty easy to just graph on paper as well because they are both linear. So if I show you, this is just a screenshot of my calculator. And the blue is the original linear line. So y-intercept at 6, you can tell the slope is -3 to the right one, down 3 to the right one. So you can check that. The inverse, the red line, starts at 2 and slope is 1/3. So down 1 to the right 3, etc. When you graph a function in blue and its inverse in red, they should reflect over the line y equals x. So I'm just going to sketch in the line y equals x here. Okay, so that would be this green line here. Inverses, functions and their inverses always reflect over the line y equals x. So if you take this blue function, for example, this point is 0, 6. If I flip that or reflect it over the line y equals x, it's now going to flip over to 6, 0. Plus, if you think about, if you have a point, 0, 6, if you switch it, 6, 0, you will get the inverse. So you can visually verify this, or I could have just graphed the blue line and taken points from the blue line and flipped them to get my red line. Okay, so another example here, easy point, 0, 2, if I flip that, 0, 2, if I flip that would be 2, 0, and you can see that on the blue. So any point, however, I mean, I can take this point here, reflect it over the line y equals x, and I would end up down here. So it's kind of a cool connection for you. All right, adding on a bit. If you graph a function and want to know if the inverse is a function, because it may or may not be, you can do the horizontal line test. Now, I know you're familiar with the vertical line test. The vertical line test will tell you that this is a function. So, for example, if I take a vertical line here, over on this one, right? If I take a vertical line and just start going through, it's a function. It's a parabola. I know it's a function. Never going to go through 2 points at once, right? If I graphed its inverse, I could tell if it's a function by using the vertical line test, or I can just do the horizontal line test on the original parabola, the original function, and I can see right away, oh, I'm going through 2 points. That means its inverse is not a function. Okay, so the horizontal line test isn't absolutely necessary. It just saves you a step. So if I would be doing, I could graph both the function and its inverse and always use the vertical line test, or I can save myself some time and just use the horizontal line test. And I'll come back to that as we look at a couple more examples here. Okay, so this example, well, actually, maybe pause the video and give this one a shot as well. So see if you can find the inverse and then graph both the function and its inverse. All right, so you switch x and y, and then you solve for y. So I'm going to subtract the 3 over. And then how do you solve for y when it's squared? You will square root both sides, or you can raise both sides to the 1/2 power. It's the same thing, as you recall, right? Reciprocal 2, and you get 1/2. Also notice the function notation, or inverse notation, excuse me. So that would be my inverse. If you graph the blue, you recognize that's a parabola with a vertical shift up 3. And then if you notice, this is a square root function with a horizontal shift to the right 3. So all stuff you covered in chapter 3. I will unveil the graph, however. So, oops, sorry, you know what? I forgot a plus or minus over here, but I can toss it in there. So this is going to look a little awkward. This is a plus or minus, right? When you square root something, you have to remember to plus or minus that. So just to clarify my graph. So the blue is the x squared plus 3, right? Vertical shift up 3 parabola. The red is a square root function, and if I graph the positive, that's the upper part of it, and if I graph the negative, that's the lower part. If I toss in the line y equals x here, you can see that the blue function reflects over the line y equals x to get your red inverse. You can probably, especially if you're visual, you can tell. Is the inverse a function? It is not, right? Vertical line test says, nope, that's not a function. The horizontal line test of the original parabola also tells me that its inverse is not a function. So there's a visual example for you as well. One quick thing on the, since the inverse is not a function, oftentimes textbooks like for your inverse to be a function. So if you look at this parabola, where would you have to restrict your blue parabola to make the inverse a function? So if you think about, if I inverse 0, 3, that's 3, 0. If I inverse any of these points, that's going to give me these. Well, I don't want these because that's what's making it not be a function. So if I restrict my quadratic to only positive x values, then the inverse is going to be also restricted to only positive x values. And I can kind of put these side by side here, right? So now, and I should have really restricted my blue, sorry. So my parabola is really only the right-hand side, the positive, and so the inverse also is only the positive. Likely your homework won't ask you to do any sort of restriction. So if you get the basic idea of switching x and y and solving for y and graphing these, you will be totally fine. Okay, one more. We'll just bring the power up a notch. So again, if you switch x and y, I'll give you a second to do that work. Switch x and y and resolve for y to find the inverse of this third degree polynomial here. So switching x and y, then adding 2. And then to get rid of a third power, you can cube root both sides or raise it to the 1/3 power. So whatever you prefer. So here is the inverse, and I should use inverse notation there as well. So this is the inverse. I also tested some points off to the side, so just to give you an idea, because this is probably one that you're not as familiar with. So I plugged in these x values into the third degree function and got these output. So just one quick visual here or talk through. -2 cubed, -2 times -2 times -2 is -8. -2 is -10. So you can kind of verify all of those if you'd like. And then I can just literally flip these from the blue function to the red inverse. So notice I just switched my x and y rather than retesting over here, because that's kind of tedious, right? So use your knowledge of just flip-flopping points if you want. So now if I go to the graph, I really could just plot these points, like -2 and -10 is way down here. -1, -3 is here, etc. And you would start to see this pattern, as well as the inverse points in red, -2, sorry, now x is here though, right? So -10, -2, -3, -1, etc., etc. And you see that red. Again, I could put in the line y equals x, and you will see the reflection over the line y equals x quite nicely on this one, in fact, right? You can really tell, like, this is reflected, etc. So there you have it.